Hello everybody, welcome to this video. My name is Hao. In this video, I will present our paper entitled High-Throughput Elliptic Curve Cryptography using AVX2 vector instructions. This is a joint work with Johann, Jiaqi, Peter, and Peter. SIMD stands for the single instruction multiple data. Essentially, any modern high-performance processor architecture supports vector extensions to enable parallel processing based on the SIMD paradigm. Typical and well-known examples include MMX, SSE, and AVX developed by Intel and AMD's 3D Now, and also the AVX for the Power PC. Taking Intel's x86 and x64 platform as a case study, the evolution of vector extensions over the past 25 years can be briefly summarized as listed. In 1997, Intel introduced the MMX extensions. It initially supported operations on packed integers using the 8 64-bit wide registers. 2 years later, Intel announced SSE, enriching x86 platform by 8 128-bit registers and dozens of new instructions to perform packed integer arithmetic. Afterwards, AVX, with the meaning of the advanced vector extensions, was first equipped in Intel Sandy Bridge microarchitecture in 2011. AVX added packed floating point instructions using 16 256-bit registers, but it still operates on the packed integer with 128-bit registers. AVX2 was first supported with Intel's Haswell microarchitecture in 2013. AVX2 enhances packed integer operations by using 256-bit registers. The up-to-date incarnation of AVX series is AVX512. It augments the execution environment by 32 512-bit registers and also brings various new instructions. Consequently, the bit length of SIMD registers increased from 64 to 512 over a period of just 20 years. And one can expect further extensions in the future. In this work, we take advantage of AVX2. AVX2 supports several SIMD fashions for packed integers instructions by its 256-bit registers. In our work, we choose to operate on 4 64-bit elements, but the multiplier of AVX2 is 32-bit. In detail, the related AVX2 vector multiplication instruction is shown here. It only multiplies the lower 32-bit of each 64-bit element and generates 4 64-bit products. SIMD instruction sets like AVX2 turn out to be beneficial for various kinds of cryptography algorithms. Using elliptic curve cryptography as an example, the implementers can take advantage of SIMD parallelism to first accelerate the field arithmetic by adding or multiplying several limbs of field elements in parallel. Second, accelerate the curve arithmetic by executing several field operations in parallel. And third, a combination of the first and the second strategy. And also he could mix using these three fashions in the entire implementation. In order to better understand these SIMD accelerations, we use the case of addition as an example. We could assume each row is the AVX2 register. As we said before, we use 4 64-bit elements in each AVX2 register. The first figure shows to accelerate the single addition by adding 4 pairs of the limbs in parallel. The second figure illustrates 4 parallel additions, and it could be used to accelerate the higher level point arithmetic. The third figure showed the combination of the first and second strategies, that is, it performs 2 additions in parallel, and each addition is also accelerated inside. And the implementers are able to use all of these parallel accelerations in his implementation. Here, we characterize the n times m way parallel implementation of ECC. It means it performs n field operations in parallel, where each field operation uses m elements of a vector. So recall these 3 cases. Currently, we could call them 1 times 4-way, 4 times 1-way, and 2 times 2-way parallelism. X25519 is widely used elliptic curve Diffie-Hellman key exchange protocol. The underlying curve is Montgomery curve named curve 25519. This curve is over the field with a prime of 2 to the power of 255 and minus 19. Basically, there are two phases defined in the protocol. One is the key generation. It relies on a fixed base scalar multiplication and is usually computed on the curve of ED25519. ED25519 is a twisted adverse curve. ED25519 and the curve 25519 are birationally equivalent. The other phase is computing a shared secret by a variable-based scalar multiplication on curve 25519. From this figure, we could basically split arithmetic of X25519 to three layers: the field operations, the general point arithmetic, for example, the Montgomery ladder, the point addition and doubling, and then, finally, the two types of the scalar multiplication. Currently, all the ECC implementations optimized with AVX series are for low latency. Here we listed the latency-optimized implementations of X25519 by using AVX vector instructions. Let's see the first two implementations. While AVX2 doubles the amount of integer parallelism compared to AVX, in theory, it is expected to decrease around 40% or 50% of the latency, but the actual reduction in execution time is much smaller, namely just around 27%. The same situation continues to AVX 512. Analogously, AVX 512 doubles the amount of parallelism compared to AVX 2. It is capable to perform operations on 8 64-bit elements instead of 4. Well, still, the reduction of the latency is only around 25%. So the benchmarking results published in this literature show the parallel implementation of X25519 do not scale very well when switching from one generation of the AVX to the next. This immediately raises the question of how implementers can exploit the massive parallelism of future SIMD extensions in ECC. The future SIMD extensions will operate on vectors maybe 1024 bits long or even longer. So going along with this how question is the why question, that is, why are fast implementations needed? Or put differently, what applications demand low latency implementations of X25519? Unfortunately, none of these papers identified a use case or a target application for their latency optimized implementations. Since many security protocols nowadays support X25519, for example, TLS 1.3, one may argue that a fast implementation reduces the overall handshake latency for a TLS client when connecting to a TLS server. The problem with this reasoning is that transmitting the public keys over the internet will most likely introduce an orders of magnitude higher latency than the computation of the shared secret. Given a clock frequency of around 4 GHz, the user will most likely not recognize an execution time reduction by a few 10,000 clock cycles. So why we research the high-throughput implementations? It could now be argued that the scalar multiplication is not only needed on the client side, but has to be performed also by the TLS server. Indeed, TLS servers of big organizations like Google or Facebook may be confronted with several 10,000 TLS handshakes per second, and a faster scalar multiplication will help them to cope with such extreme workloads. However, what really counts on the server side is not the latency of a single scalar multiplication, but the throughput, that is, how many scalar multiplications computed per second. Given this requirement, would it not make sense to optimize an X25519 implementation for high throughput instead of low latency? And what throughput can a throughput optimized implementation achieve compared to a latency optimized implementation? To our surprise, it seems that both questions are not answered by the existing literature. This work takes the first step to answer these questions and introduces a throughput optimized AVX2 implementation of variable-based scalar multiplication on curve 25519 and fixed-based scalar multiplication on ED 25519. Our implementation performs a 4 times one-way parallel scalar multiplication, which means We perform 4 scalar multiplications simultaneously in a SIMD fashion. Well, each one of them is independent of each other, and each one executes the same instruction sequence. And each instance can use a different scalar, and in the case of curve 25519, each instance can use a different base point. In each scalar multiplication, the point arithmetic and the underlying field arithmetic use only a single 64-bit element of a 256-bit AVX2 vector. We could say that this is a coarse-grained form of parallelism. And it has several advantages. First, it is easy to implement. We could just simply vectorize a reduced radix implementation of X25519. Second, it is easy to audit. And third, this type of the parallelism could support various SIMD extensions, not only as AVX2. Especially there is no dependency among different parallel instances. Our method should scale better, for example, from AVX2 to AVX512. For the field element, they are 255-bit large integers. Most previous AVX implementations take advantage of a classic representation of using 25 or 26 bits per limb. As shown here, each limb Fi is either 25 or 26 bits long. Well, in our work, we employ a radix 2 to 29 representation for the field element. That is, each limb Fi is 29 bits long. This turned out to be the best option for our 4x1-way scalar multiplication. For example, in the previous AVX2 latency-optimized implementation, it mainly uses 2x2-way parallelism. In their case, both two representations require 5 limbs for each field element. However, as we introduced before, our implementation is in 4x1-way. In this setting, radix 2 to 29 will save 1 limb compared to the other representation. This would help us to save a lot of subsequent instructions during the computation. Since our implementation is 4x1-way, 4 field elements are actually packed in a vector set. Each column is a AVX2 register in this figure, and we call it limb vector. Each limb vector contains 1 limb from 4 different elements. And notably, the limb is located at the lower 32-bit of each 64-bit element. Because as we expand before, the multiplier of AVX2 will only multiply the lower 32-bit of each 64-bit element. Okay, now let's turn to the arithmetic in the underlying field. Since the 4 parallel instances in our implementation execute the totally same instructions, we here could just take the routine of single 64-bit line to explain. Because radix 2 to 29 is able to represent a 261-bit integer in theory, in order to facilitate the field operations, we set the modulus p to be a multiple of the original modulus during the computation. The addition is implemented in a straightforward way, that is, just an ordinary integer addition without modular reduction. For the field subtraction, we add 2p to avoid any negative intermediate values. Besides, we developed 2 types of field subtraction. One is an ordinary subtraction, and the other one is a modular subtraction. We observed that our software does not strictly require each subtraction to perform the carry propagation and modular reduction. Therefore, if we use ordinary subtraction properly, that is, to not cause overflow, the implementation performance will be improved. Modular multiplication is usually regarded as the most critical field operation due to a high frequency of use and a relatively large latency, which deserves more care. I will show the details later. As for squaring, it can be considered as a special case of modular multiplication where 2 operands are the same. We developed the squaring based on the same design rationale of the field multiplication. Okay, now let's focus on the field multiplication. Ideally, we'd like to make full use of the execution ports of the CPU. Then many instructions can be handled by different ports in parallel, and in each clock cycle, there are new instructions to be handled by ports. So it could accelerate the entire field multiplication. But due to the dependencies among the instructions, this is not easy. So in other words, we would need to reduce the sequential dependencies among the instructions, then it is able to better exploit the execution port. However, turning code to weakened dependency chains sometimes will import extra instructions and in return slow down the software. Finding an optimal multiplication strategy which schedules a reasonable instruction sequence and fully exploits the port's parallel processing ability is a very challenging task. Taking into account the different latency and the throughput properties of various AVX2 instructions, we conducted experiments with a dozen self-developed candidates of model multiplication. At last, a benchmark of all the candidates told us which one is the fastest. The distinctions among these variants include but are not limited to: first, the model Q reduction is either separated or interleaved with the multiplication, and if interleaved, how to interleave both. Second, the different plans of the carry propagation. Third, whether and how to store intermediate values in local variables. This is the winner of this candidate. It performs product scanning multiplication and the model reduction separately. It takes advantage of a local array T to keep intermediate products generated in the first loop. There's no dependency chain in the first loop, but there are dependency chain in the second loop regarding updates of the accumulator. This figure showed that there are two steps. One is multiplication and then the model reduction and the conversion. And this figure showed that the four instances are independent with each other. For point arithmetic, we just take advantage of the state-of-the-art techniques to directly construct them by our field operations. Just as we said before, we developed two subtraction variants. Take the point addition as an example. Two subtractions can be performed as ordinary subtraction, and only one must be the modular subtraction. In this way, it saves around 5% latency than using three modular subtractions. Our source code has a fixed instruction sequence without any conditional branches, for example, the if-else statements, so the implementation is constant time. We measured the performance of our software on both the Haswell and the Skylake CPUs. We use C-long compiler with a version of 10 to compile our source code, and the turbo boost and hyper-threading features were disabled during performance measurements. Even though the previous low-latency AVX2 implementation, that is the work of Hernandez et al., uses 2x2 way to implement a variable-based scalar multiplication, but there were timings of some 4x one-way operations reported in their paper. Compared with their 4x one-way multiplication, our multiplication saves 37 cycles on Haswell and saves 17 cycles on Skylake. The overall performance of our software is shown here. On Skylake, our software can compute around 100,000 key generations or 32,000 shared secrets per second on a CPU clocked at 2 GHz. Because the frequency of two CPUs are different, we compare the performance directly from the CPU cycles. The experimental results show the throughput capacity of our software is actually around 30% stronger on Skylake than on Haswell platform. Okay, let's compare our implementation to other low latency implementations. In order to have a fair comparison with others, we also compile other source code and measure the timings of others' implementation on our own machines. If their original compiler is C-long, we use C-long 10 to compile their code. And if they originally used GCC, we would use the GCC 8.4, which was launched earlier this year. Their original performance data is on the upper row in the table, and the timing measured by ourselves is on the lower row. It is easy to be recognized by the CPU or the compiler as well. So compared with other implementations on Haswell, our work increased the throughput of key generation for 60% and the share secret for 45%. And on Skylake, our software has 70% more throughput for key generation and 50% more for shared secret. To summarize our work, we find that AVX2 offers great potential to optimize ECC, and all existing implementations used AVX2 to minimize the latency of a single scalar multiplication. Our work is the first to use AVX2 to maximize throughput, that is, maximize the number of scalar multiplication per second. Our implementation improved the state of the art by a factor of 1.5 to 1.7 for the throughput, and we can apply a straightforward extension to AVX512. For example, in that case, our software will perform 8 scalar multiplications in parallel. Okay, since as we said, the optimizing for low latency does not scale very well when switching from one generation to AVX to the next. So we would like to make our software to support AVX512 and see the improvement of throughput, so to see how it scales. And moreover, we would like to apply our method to isolated-based cryptography. That's it. Thank you for your attention, and welcome to have a look of our code.